a 2,000 kilogram car is driving horizontally at 15 meters per second. The driver slams on the brakes and the car skids to a stop. The question is, how far does the car travel while stopping? So it comes to a stop, having initially been traveling at 15 meters per second. Well, the force that stops it is kinetic friction. The coefficient of kinetic friction is mu k, and it's equal to 0.7. Again, we're solving for delta x. We're going to use energy considerations to solve this. Draw a force diagram. There's the normal force. Here's the weight. Remember that weight is m times g. And then if it's moving to the right, kinetic friction is pointed to the left, opposing the motion. Now, I'm not going to calculate the weight yet. You can, all right? It's 2,000 times 9.8. But I want to just prove something. So I'm going to take this a little bit further, and you'll find out that the mass actually cancels if you go far enough. You don't have to do it this way, but I just want to. You could go ahead and calculate the weight, like I said. The reason why you would calculate the weight is to calculate the normal force, which allows you to calculate the friction. So, the initial energy plus the net work equals the final energy. Well, the initial energy is made up of kinetic plus potential. The only force here that does any work is friction, and it works against it. Normal force is at 90 degrees. Remember, the cosine of 90 is 0. So you have the work due to friction. And then afterwards, final kinetic energy plus final potential energy. Now, a lot of this stuff's going to cancel out. You have no change in height, and so we don't need the potential energy terms. And it comes to a stop, and so that's 0. So what we end up with is that 1/2 times the mass times the initial velocity squared, and that's kinetic energy, right? 1/2 mv squared, plus the force of kinetic friction times the displacement times the cosine of the angle between the displacement and friction, which, remember, that's going to be 180, and so the cosine of 180 is -1. That's going to equal 0 because it comes to a stop, and we don't have to consider potential energy. All right, so let's put in some numbers here. This is 1/2. Well, you know what? No, I'm not going to put in numbers yet. 1/2 mvi squared. Kinetic friction. Okay, see if you can follow me here. Kinetic friction, let's write this in a different color. I'll write it over here. Kinetic friction is mu times the normal force. That's mu k times the normal force. Well, in this case, the normal force is equal to the weight, right? In the y-axis. The weight is mg, so the normal force has the value of the mass times g. So I'm going to substitute that in here. And I'm going to take all of this and put it in here. So mu times mg, that's your friction, times delta x, times -1, because remember the cosine of 180 is -1, and for friction it will always be -1, equals 0. Look what happens. If you divide everything by mass, the mass goes away. 0 divided by anything is 0. The point being that the distance it requires to stop is independent of the mass. If that makes you truly uncomfortable when solving a problem, you have to have mass and I don't give you a mass, make one up. You can use 1 kilogram, that would be my advice. You could use 10 kilograms, 100 kilograms, a billion kilograms. You'll get the same answer for delta x. So now I have 1/2 vi squared plus mu times g times delta x times -1 allows me to bring this to the other side and then solve for delta x. So I'm going to solve this as such. Mu times g times delta x eventually equals 1/2 vi squared. I know that looks totally gross and awful. You just have to start here and work through it. Now substitute in the numbers. Mu is 0.7 times 9.8. Then there's your delta x, and that's 1/2 times 15 squared. One of the main points, and the reason why I do this in class instead of just solving everything to the side and substituting in, because I want to point out that displacement in stopping is proportional to the speed squared. If you're traveling twice as fast, and you square that, it takes 4 times the distance to stop. If you're traveling 3 times faster than some speed, and you square that, that's 3 squared is 9. The stopping distance is 9 times greater. 9 times greater, that's a lot. So that's one of those things for life. Stopping distance is related to the speed squared. Anyhow, let's solve this problem. I need my calculator. Okay, now. I get approximately 16 meters. I do want to just say that you could have solved this, and it probably would make a lot more sense to you if you just went off to the side and calculated the friction, got a number for that. You've got, that's 0.7, that's 2,000, that's 9.8. Get a number, just plug it in here. You know that that's what you're looking for. That's -1. You know the mass, you know the speed, you can get a number here. That would be a lot less confusing, but I did just want to make the point that delta x, the stopping distance, is proportional to the speed squared.